Well, I'd like to welcome everyone back. It's good to see you all. I hope you all had a nice Thanksgiving break. Welcome to our Pilina webinar series, our November edition. And we're very pleased to have Dr. Karen Meech joining us again for a repeat performance from the Institute for Astronomy. Grateful she was able to join us again. Dr. Karen Meech is an astronomer / astrobiologist who investigates how habitable worlds form, exploring the bigger picture of whether there is life elsewhere. Her work has embraced the power of interdisciplinary science, and she's combining geological fieldwork, geochemistry, astronomical observations, theory, and space mission concepts to address fundamental questions about how Earth got its water. She began her career in physics and astronomy with an undergraduate degree in space physics from Rice University and a PhD in planetary physics from MIT in 1987, studying comets, after which she joined the faculty at the University of Hawaii. She served as the graduate chair as well as the interim director for IFA. Karen has won many awards for her work. She was co-investigator on 3 Comet missions, including Deep Impact, Epoxy, and Stardust Next. She's been leading the development of a space mission to study icy material in the asteroid belt, and led the team to characterize the first interstellar object that was discovered passing through our solar system. And so at this point, I'll pass our time over to Karen for her presentation on forming a habitable world. Where does the water come from? Thanks again for joining us, Karen.
Well, thank you very much for the nice introduction. So, as you've heard, my background is in comets, although nowadays I'm really focusing on big picture questions related to astrobiology. So I'd like to start with this beautiful picture from space. Nowadays, in the modern era, with the advent of the space age, we have a very different view of the universe, especially now with JWST showing us these spectacular images. But some of the fundamental questions are the same. Some of the things that we saw at the beginning of the space age are generated by this beautiful picture. This was taken on February 14th, 1990. Here's the Earth as seen from 6.4 billion miles away from Earth. And the planet at this point looks like a pale blue dot. All of this light is just scattered light here. And as Carl Sagan said in a book by the same title, our planet is a pale blue dot in the dark, and the Earth is the only world known so far to harbor life, and this is likely because of water. And as we all know, life requires water. Our cells are mostly made of water, and the energy of life's chemistry is a process that requires water. Water is also very special to life because it has a high heat capacity, which means it stays liquid over a very wide range of temperatures, and this is important for habitability in our solar system and elsewhere. Now, when you ask kids where water comes from, and I've given a version of this talk for second graders, everyone raises their hand and they say it's rivers, lakes, oceans, clouds. And I say, well, that's where it is on Earth. Where does it come from? And usually the kids are very enterprising. They say, well, you were introduced as an astronomer, so it must come from space. And so in fact, water is made in space. This is a beautiful image of a cloud of gas and dust in the process of forming stars. In the deepest part of the clouds, it's very, very cold. There's not much energy entering into these cores of the clouds. And the tiny little dust grains that are there that have been formed in the death throes of stars actually start to have ices freezing out onto their surface. If they get a little bit of energy, some of these molecules can move around and you can get a little bit of chemistry. And this is likely where water forms. Of course, it's a big leap then to ask the question of how does it get to its familiar form to us on Earth? Now, of course, water is very important for astrobiology, and the whole field of astrobiology is relatively new. And it's a field that is seeking to understand how you make a habitable world. How do you make a world that's suitable for life? How do you make a world that can have the right mix of water, organic compounds, a rocky planet that's at just the right temperature? So ideally, we would like to astronomically observe this process. We don't quite have the technology. This is one of the state-of-the-art arrays of telescopes. This is called ALMA, the Atacama Large Millimeter Array. This is in the high altitude deserts of Chile. And this can start to image the process of planetary birth. So this upper picture is effectively a radio wavelength image of another star system that's in the process of forming, a young sun in the middle. The problem is, if you look at the scale on here, it's huge. Astronomical unit, as a reminder, 1 AU is the average Earth-Sun distance. So what we're seeing here is much larger than our solar system. This is predominantly an image of dust, and these dark lanes are probably where a young planet has formed and is scooping up the dust during the formation process. This isn't quite good enough to look at how planets like ours has formed. We think the next generation of telescopes that come around in the 2030s with proposals that are going in will get much finer resolution. We can start to peer into the region where the rocky planets form, not only watching the process of their birth, but maybe even getting information about chemistry or imaging the planets. Now, this is important because as of today, we have well over 14,000 extrasolar planets, planets in other solar systems that are either confirmed or candidate planets, almost 4,000 planetary systems. And of these, maybe 50 or so are potentially habitable. So understanding what is the process that makes these bears on the big question of how much life might be out there. Of course, right now, we have only one system that's habitable and inhabited that we know of, and that's ours. So just a reminder about the architecture of our solar system. We have the rocky planets relatively close to the sun, one of which is in what we call the habitable zone. And when astronomers say habitable zone, the formal definition is this is at just the right distance from the star so that water would remain liquid on the surface of the planet if it had an atmosphere. So Earth is in the habitable zone, Venus is just inside, Mars is just outside. We have the asteroid belt, and then outside of this, in the very cold outermost region of the solar system, we have the gas giants. Now, it turns out this planetary architecture may not be very common with rocky planets inside, gas giants outside. As we start to look at the statistics of all these other planetary systems, we see that by and large, they look very different from ours. So this graph is just plotting the orbital period. Remember, Earth is at 365 days. This is one Earth mass here, so this is going up by a factor of 10 for each tick mark. Here's our rocky planets. We don't see extrasolar planets that occupy this part of the graph. Here's our gas giants. We see a lot of very large planets close to the star. We see a lot of planets that may still be rocky, but are supersized. And so is there something special about the architecture of our solar system which made our world just right? So how are we going to look back in the past and understand how our solar system formed? Well, the way we do it will be much like an archaeologist. We have to look at the leftover remnants of the process of planetary building. And these, by and large, are the small bodies that are left over. And we want them to be small because that means they will have never been heated. And they're sort of a fossilized remains of what happened as our solar system was being born. The sort of objects that we will be looking at are asteroids, especially the small ones. And these are some beautiful close-up images of visits that have gone to asteroids. Some of these very recently, the Bennu and Ryugu, with the recent space missions that are bringing samples back to Earth, some that were farther in the past. And this also includes meteorites, which are fragments from asteroids that have made it all the way to the surface of the Earth. In addition to asteroids, we have comets. And of course, that's where I started my degree, was looking at comets. These are small bodies just like asteroids, but they differ in the fact that they've got a lot of ice. And so, of course, I had to show a lot of beautiful comet images. What happens to make the comets look so spectacular is that as they come closer to the sunlight warms up the ice, and the ice converts directly from an ice to a gas process called sublimation. And because they're relatively small kilometer scale bodies, the gas has enough pressure to just push the dust completely off of the comet's surface. And then what we see from Earth is sunlight reflected from both the solid body and the gas and dust that's spreading away from the comet. When you have a true color comet picture, the yellowish portion is reflected light from the dust, and the colorful bits are light interacting with the gas, much like the fluorescent light bulbs in your office. And then the colors tell us something about the chemistry. So getting back to what does life need? Well, it needs the organics that provides the energy for the life processes, and it needs just the right amount of liquid water. Now, water is a really abundant molecule in the universe. And in fact, if you just took a mixture of gas and dust that has similar composition to the sun and our giant planets, and you froze it, you should have worlds that are just completely rich in water. But when you look at our inner solar system, it's actually quite dry. Mercury has very little water. There's some ice at the poles. That's probably because comets collided there and then froze in the cold regions. Venus today doesn't have water, but it must have had similar amounts to Earth, but it's undergone catastrophic climate change, which has left it super hot, inhospitable world. We look at our pale blue dot and it looks like it's a watery world, covered 75% with water, but we actually don't have that much water. The moon is dry, there's a little bit of water at the poles subsurface, and Mars is almost dry, but it may have had a lot more in the past and lost it. So if you have too little water, it's really hard for life to start, but if you have too much water, it's hard also. You know, some of the state-of-the-art ideas about how life starts, it's believed that you need cycles of wet, dry in order to concentrate the molecules that will become part of the life processes and get them to form layers and films that will eventually become life. Now, if you have too much water, we get into some real problems. So here's an artist rendition of a water world. You may have seen the movie years and years ago with Kevin Costner, where Earth is completely covered with water. If we had as much as 5 times the amount of ocean water that we have, we'd be in trouble, because that would mean all of the dry land would be covered. And the reason this is a problem is that we have this wonderful silicate weathering cycle, carbon silicate weathering cycle on Earth, where volcanoes spew out water, carbon dioxide, all sorts of other chemicals into the atmosphere. This gets into our clouds, and some of this will form acid rain, which will then help dissolve the minerals, freeing up some of the valuable minerals that life needs, like phosphorus. And then this gets cycled into the oceans, and then when the continents collide, it gets recycled. All of these on different timescales. This whole recycling system completely shuts off if we have no dry land. Even worse, if we had 50 oceans worth of water, the pressures at the bottom of the ocean would be so high, there would be a thick ice layer. And we think you need the interaction of the rock and water for a lot of the chemistry for life. So we have to have just the right amount of water. It can't just be some water. So let's start with an overview, a very brief look at how you make a planet in general, and then take a look at Earth. So when we're making a solar system, again, we start with this cloud of gas and dust in space. It somehow starts to collapse. It could be that it collides with another cloud. There could be a nearby star that explodes and causes a pressure wave into the cloud. But once it starts to collapse, it will begin collapsing into a flattened disk, where as more and more material falls into the center, it gets warmer and warmer. One important concept about this, if we zoom in and look at the disk, here's the young star that's forming. There's a hypothetical boundary in this protoplanetary disk of gas and dust that we call the water ice line. Inside of this, it's too warm for there to be any ice at all. Instead, the water's in a vapor form. Outside of this line, it's very cold, and you can have a lot of ice. So as time goes on, all these tiny little particles and dust grains start to collide with each other, and you make bigger and bigger and bigger bodies until eventually they become kilometer scale. Then we're starting to call them planetesimals, or the building blocks of planets. They eventually grow large enough that you get rocky bodies and the cores of the giant planets. Once you're big enough, you can gravitationally start to capture gas, and this is how the giants get so big. The final stages of the solar system process, any of these small planetesimals that get close enough to the giant planets, the gravity from the giant planet will alter their orbits, and it can fling them either towards the sun or out to the outer solar system. So this little movie shows what that process might be like. So here you have a small planetesimal, it's orbiting near the sun, has an encounter with Jupiter, and it gets flung into the outermost regions. Some of them might escape, but most of them end up getting trapped in this vast cloud that we call the Oort cloud, which might be 50 to 100,000 Earth-Sun distances. Later on, they may encounter a nearby passing star, get a little nudge into the inner solar system, and we'll see them as a comet. So that's the basic process. But if we want to look into a little more detail about what early Earth looked like, it was a pretty violent process. Early Earth was a very hot, inhospitable place, in part because of all these collisions that are forming the Earth are releasing energy. So for a long period, we may have had a molten surface on the planet. It would probably take at least 1 million years to solidify. Once it did, this is much more dense than the underlying molten material, and it would overturn and sink down to the core. That will be an important thing to note for later. Now, during this time, all of this molten material, it's hot and it's outgassing any of the gases, which include water. So it may have looked like this in some of the early stages. Now, normally I had a picture in here of just some random volcano, but I thought I'd advertise. One of our faculty, Mike Connolly, took this a couple of nights ago. This is the eruption on the Big Island on Mauna Loa, as seen from the road going up to the Mauna Kea Observatory. It's just beautiful. Here you've got the fire fountains and some of the steam coming off. So as the planet now starts to cool, a steam atmosphere will form, and eventually this can result in oceans in another 5 to 10 million years. But where did this water come from that's forming our oceans? So I like to start with, what do we actually know for sure? Well, we know two things for sure. One of which is we know how long ago this started. We know the age of the solar system to great precision. Our solar system is 4.567 billion years old. And we know this by looking at meteorites. You can slice them open. I didn't put a scale bar on here, but this is probably less than 1 millimeter across completely. All these tiny little circles in here are some of the first solids that actually condensed out of the hot gases near the star. And we can actually date these in the lab. And all of these early solids date to the same age. So that's when things first started to get going. We've also sampled this by collecting material from comets. So that's one fact that we know. Another data point is that we know that by about 200 to 300 million years after the start of our solar system, we had oceans on Earth. And the way we know this is by two facts. One is when you look at some of the oldest rocks on Earth, largely found in Australia, and you look at some of the tiny mineral grains, it's clear that some of these represent volcanic eruptions that had to cool off extremely rapidly. And the best way to do that is if they're erupting in large bodies of water. And when you date these minerals, they're called zircons, from all over in the oldest regions. They're all clustering around 4.3 billion years, the oldest ones. A second marker that tells us that we had oceans is when you look at some of the old rocks in Canada. Most of these rocks are granites, and granites can't actually form unless you have cycles of volcanic eruptions in water, and you get a lot of recycling and you're changing the chemistry of the magma. So sometime between T0 and 200 million years, we got water. So what are the possible sources? One is, well, Earth was forming inside the snow line, very hot. Couldn't it just capture gas directly? You know, the tiny little dust grains that will eventually be the building blocks of planets. Maybe the gas molecules just stuck because they're very porous at the beginning. And this certainly probably happened, but as things start to get bigger and bigger and collide, the velocities of collision get higher and higher. So the question is, can they keep it? And could you deliver enough? This would have happened very early. Another idea that was put forward by the Japanese is maybe Earth made its own water. And what do they mean by that? Well, when we had a molten magma ocean on the surface, if we had an atmosphere of hydrogen gas, they could have chemically combined hydrogen with the oxygen from these oxides in the magma, and you could manufacture water. They've tested this in the laboratory. They've shown theoretically this would work. But again, is it enough to bring the water we see on Earth? Then one other constraint here is we don't know if we ever had a hydrogen atmosphere, and that could have only lasted maybe 10 million years. And we don't know if it occurred at the same time as molten oceans. Perhaps the most obvious one is, well, Earth formed inside the snow line, but why not have things that formed outside that are icy just get thrown inwards, smack into Earth, in other words, comets, and that could deliver water. And we certainly see evidence of all of these collisions by looking at craters. This is a crater on the moon. Here we have one on Mars. These are some on Jupiter's icy satellites. So we have evidence that things were flung around a lot. So how are we going to distinguish these? Well, we need some sort of chemical fingerprint or marker to see if we can trace the path of water. And an idea came up early in the 1960s and 70s that was generated by the fact that people had noticed Earth's ocean chemistry of the water was a little bit different from what was expected. And this is what they were looking at, the H, or the hydrogen component of water. Now, as we all know, atoms are made of a nucleus that has a proton that's positively charged and a neutron, and then electrons orbit the nucleus. If you have an extra particle in the nucleus that's not charged, but just adds mass, this is called an isotope. They're chemically the same, but one is heavier. And these are very important in astronomy and in biology because of the different mass. They interact differently chemically and with life. So what scientists had noted was that the ratio of the heavier form of hydrogen, deuterium to hydrogen, or the D to H ratio, was about 6.5 times higher than what we thought the solar system's starting value should be. And they had estimated this by looking at the particles flowing from the sun, by looking at gases nearby to our solar system. So then in 1986, the Europeans sent a space mission to Comet Halley, the Giotto mission, and they actually flew through the tail, and they learned that comets are mostly made of organic compounds, water, carbon dioxide, carbon monoxide. But they measured the D to H of water in this comet, and it was about 2 times higher than the Earth's ocean. So people said, aha, obviously comets are delivering Earth's ocean water. Well, then another comet was measured from the ground, a few more, and they were all pretty high. So clearly that can't be the only source because it doesn't really match. So people started to look at the other primitive bodies that we study, namely the meteorites, and they had a range of D to H values, some equal to Earth's ocean, some lower, some higher. So in order to untangle this, if we're using this as our chemical fingerprint, let's examine these values a little bit more closely. The solar system starting value, people started to look at the D to H ratio, initially not by observing it, but by looking at chemical reactions. And in the early 1980s, 1990s, the chemists had noted by looking at all the possible chemical reactions you could have at these low temperatures in space, it was much easier to form molecules with deuterium, took much less energy. So they knew the process. that would create these high values. As we get a little later in time, as people have much more sophisticated models, they realized, oh, we've got all these layers of different temperature in the young solar system when there's still gas and dust around. There's a hot surface that gets irradiated by the star. There's a warm layer where a lot of the chemistry occurs. And then in the middle, it's very cold. And they started to make really sophisticated models where the sun is here at this corner of the graph, and the different colors represent the D to H ratio. Red means higher. Well, this would suggest as long as it's cold, you get higher D to H, so cold is farther from the sun, but it looks like it's pretty complicated. We don't yet have the technology to look at this level of detail in another solar system, so we're relying on the models. What this probably means is we don't really have a clue what the solar system started with, because it's variable throughout the solar system, and it's variable with time. And it's probably different for different chemical compounds. So what about comets? How do we measure it in comets, aside from sending a spacecraft there? Well, after the Giotto mission measured it in a comet, people started to observe it. And in fact, some of the first ones from the ground were from Mauna Kea at radio wavelengths. And so this required really bright comets. And so you get one every few years. Nowadays, the Keck 10-meter telescopes can observe them to fainter comets, but still, we maybe only have about a dozen. And all of these, if this is Earth ocean water D to H, all of these comets were too high. But these were all comets that we thought formed in about the same region. So people were really excited to look at a comet that now spends a lot of time in the inner solar system. And they think those actually formed at even colder regions in the solar system. So I said, all right, great. It's going to be a really high D to H. The first ones measured were low. So they go, all right, we have to redo all of our models. How can we get low D to H at colder temperatures? So they made some models that figured it out. Then the next one they observed, same type of comet, it was the highest they'd ever seen. So then the astronomers throw up their hands and say, we don't know what D to H of comets is. So let's just put a big question mark here. We don't really know what it is. How about the meteorites? How do we observe these? Well, these are pretty easy. We've got thousands of them. We can bring them into the laboratory. This is actually an image of the lab in the basement of the post building. So this is the Keck Cosmochemistry Laboratory, a multi-million-dollar machine that can do very detailed isotopic measurements at a millionth of a meter scale in thin slices of meteorites. So measurements like this have shown here, this is just D to H again. Here's where comets fall. Here's where Earth oceans fall. And these histograms show measurements of meteorites. And you can see the most abundant ones are at Earth's ocean level. So why aren't we just done? Meteorites, asteroids could have hit the Earth. Doesn't that explain it? Actually, no, because meteorites have other chemicals in them, some of which don't match the Earth's signature. So I think we're going to have to put a big question here. Well, what about the Earth's ocean? Certainly, we understand the D to H of the ocean, easily accessible. We can go get it, grab it, bring it into the lab, and measure it. Well, not so fast. A few years ago, actually, 2007, the chair of the oceanography department here at UH, Mike Model, worked on a review paper to first assess how much water do we actually have on Earth. And it turns out we don't really know. So he broke it into various regions of the Earth. We've got the ocean and atmosphere. This we can estimate. You can estimate the volume of the oceans. You can sort of add up all the rivers, streams, how much moisture is in the atmosphere. And so everybody pretty much agrees that we've got about 1.3 ocean volumes of water on the surface. What about inside? Well, we can dig down to maybe 4 kilometers in the crust and make measurements. Beyond that, as you go deeper into the mantle, we're relying on first laboratory experiments and theory. Lab experiments, they take minerals and squeeze them into really high pressure, high temperature states that are like what we see in the mantle. And there's actually a facility on campus that can do this. and you can measure the amount of water it could have in the minerals. If you want to go deeper, then you're looking at earthquake data, seismic data, and the seismic data says there's water there. So in fact, when you look at the people who estimate on the low side, it's about 1.5 oceans of water total. On the high side, it's 11 oceans of water. But the Earth could have a capacity of maybe 60 oceans of water. So my thought is, if there's more water inside the Earth, maybe measuring it in oceans is not the best place to measure it, because this has interacted with biology, the atmosphere, and it could have changed the D to H. So I went to an astrobiology conference in 2004 in Iceland, and like many conferences, there's a tour afterwards. And I went on the tour, and one place we visited was a geothermal field, and the geologist who was with us said, "Oh, it's okay, you can go over. It's just water vapor. It's not hot. It's primordial gas escaping from inside the Earth." And so I had that kindergarten aha light bulb go on. It's like, wow, this is primordial water. That's what we should measure. So when we got back from the tour, I went to the University of Iceland and talked to some of the geologists and said, "Can we measure this primordial water?" And he said, "Well, first of all, she was wrong. That's not primordial water. That's rainwater that gets into the geothermal system, gets heated up and comes out as steam." So I was very disappointed. He goes, "Well, wait a minute. We have evidence of primordial gases coming from the deep Earth near the core mantle boundary, and this may be a result of that early magma ocean that solidified and sank down to the core." He said at certain hotspots around the world, like Hawaii, like Iceland, we can preserve some of that material without it mixing inside the Earth, and it comes up to the surface in really high temperature minerals. And I said, "Wow, this is spectacular." They said, "We know that we've got things that match interstellar space, other chemicals." I said, "What about D to H?" He said, "Well, that would be a really hard measurement. You'd need one of these state-of-the-art ion microprobes." And I said, "UH just got one." So that led me, instead of using a telescope, I went out in the field with a volcanologist and rock hammers. And when I first saw this landscape, I said, all the rocks look the same to me. How do I tell them apart?" And he said, "That's why you have me along." And I told him, "Well, that's not a very good learning experiment. You've got to tell me what I'm supposed to look for." So he eventually did. And then you bring the rocks back, and this is probably a millionth of a meter, micron across here. We're looking at these tiny little minerals to look at the D to H. And so one of our postdocs did this, and what she found was the interior of Earth is not the same as the oceans. It's much lower. So here we're looking at the solar system starting value, the comets again, and inside the Earth, it's lower. And this was only an upper limit. We do want to get more data. So with this, I think we really can confidently say we also don't know Earth's ocean. So everything on here now are beautifully constructed scenario of how we're going to figure it out. We seem to know nothing. So let me pause here and give you some takeaway numbers from this exercise. Well, first of all, I suspect that the water probably came from a bunch of different sources, and it may be a matter of how much came from each source and from at what time. But, a lot of people said, "Well, aren't you hoping it'll be comets because that's what you started with?" I don't care. I'm just keenly interested in how did we get water, because it applies to other worlds. So in fact, maybe we're eventually going to learn more from the exercise than the actual answer. But I did want to show you the numbers of where we are today. And maybe we'll have to edit this slide out of the video, because this is unpublished work and I don't want this shared. But here's the state of the art right now. These are the percentages from each of these sources. We've got comets, wet asteroids, the gas in the solar nebula, and chemical reactions on Earth. And I really shouldn't have put two significant figures here, but nevertheless, these are definite numbers that we've got right now. So now what? I love this cartoon from Disney Pixar because it kind of reflects, like, we seem to have a bit of a conundrum. How are we going to figure this out? Well, remember, the formation of a solar system is not a simple process. So this is a little bit better cartoon. In the background, we have the nice artist rendition of what our young solar system might have looked like. This cartoon here is showing us the range of temperatures in this protoplanetary disk as it collapses. It's collapsing faster in the middle where there's more material. So you can see the surface again is really hot. It's getting direct X-rays, ultraviolet, direct sunlight on the surface. Again, we have the warmer layers as we go deeper into this disk, and that's where a lot of the chemistry is happening. And then it freezes out. Any of the gases, when they get down to the middle where it's really cold, they freeze into ice grains, and they may freeze onto the dust grains. So you will get a chemical fingerprint that's different depending on where you are in the disk, because any of these chemical processes or things that might change the isotopic composition depend really strongly on temperature. So they're freezing out on the grains, but remember, the tiny little grains can move around pretty easily. Once they become planetesimals, if they get near a giant planet, they get thrown all over the place. So everything is getting mixed up. So we've got forming the fingerprints and then it gets scrambled. So what do we do about this? Well, in 2017, there was a really nice clue that got everybody excited. And this was from the community of folks that study meteorites. And this is a figure from Thomas Cruyer's paper. And so basically what he found, he was looking at different types of meteorites that formed very, very early in the early solar system. And he found something odd. They all had the same ages, but they had very different isotopes. You know, in many of the isotopes, this happens to be titanium versus chromium. The important thing was that they were two distinct groups. And this was puzzling at first because while the materials are still tiny micron-sized dust, they can easily flow in towards the sun. So they should mix. So you should have a range of values. How do you keep them separate? So what they proposed was that maybe Jupiter formed really early, and this background image is one of those beautiful images from ALMA, so it's an actual protoplanetary disk in another star system. And so you can imagine Jupiter forms early, it sweeps out material, opens a gap, and when it does this, it stops the flow of material inwards. So the only way for stuff to go beyond this is once it becomes a planetesimal kilometer scale and it gets close enough to Jupiter that Jupiter's gravity changes the orbit. So the idea is that Earth, which formed inside where Jupiter formed, so in the hot portion of the disk, either it got its water just from the gas that was there and maybe any organics that were there, or it got delivered from material that was thrown in by Jupiter. So one thing that we could use to test, if Jupiter threw things inwards, it threw them everywhere. They would crash into the sun, they would hit the rocky planets, and some of them would get trapped in the asteroid belt, where they remain today, and we can still study them. So I think the solution is to actually go to the asteroid belt and look for water there. So do we have water in the asteroid belt? Well, the answer is yes. Some discoveries from Mauna Kea beginning in the 1990s showed that we have these creatures called main belt comets. They orbit in the asteroid belt, but they develop comet tails. Anytime they get a little bit closer to the sun, they start to develop a tail, which means they have ices that are pushing the dust from the surface. So these are things that we'd like to explore. And what we would want to do is send a spacecraft directly to these main belt comets and use very sophisticated instrumentation to measure the isotopic composition of the gases, not only the D to H, but various other species like carbon, oxygen, nitrogen, because they're all temperature dependent. That gets the gases. But if we want to do the same experiment that Creuer did, you have to look at the minerals. And for that, you would want to bring a sample back to Earth to study the pieces, just like OSIRIS-REx is bringing back from asteroid Bennu, and that the Japanese brought back from their asteroid Ryugu a little while ago. So I think really understanding how Earth got its water is a very interdisciplinary process. It's going to require astronomy, geochemistry, chemistry, all of these different fields, meteorite science, and they're all playing a role. And Hawaii's research is playing a leading role in many of these areas. And I think it's going to require sending a spacecraft to objects in the asteroid belt, because what we really want to understand is where the young primitive Earth got its water, because this will have very far-reaching implications for how you form a world that, even if it's in a habitable zone, got the right ingredients for life. Because if it requires a solar system built just like ours, maybe life isn't prevalent everywhere. Now, when I'm given this, sometimes people ask, yeah, but that's really expensive. Are you really going to spend that much money to answer this question? So let's look at how much it costs. And I haven't updated this lately, so I haven't put inflation in, but you'll get the gist. So these were the actual costs of some of the Comet missions. Giotto, that was the one that visited Comet Halley. That was an expensive one at 2.6 billion. Some of these others are at the 30 million up to 300 million. The Dawn mission that went to 2 asteroids was almost 500 million. And a main belt comet mission would be a little more expensive than that. Compare that to the really big missions, things that go into the outer solar system, the Apollo program, estimates for Mars manned mission. So in comparison, going to a main belt comet is relatively inexpensive. And how much will it cost you? And I've asked this to the little kids. So assuming you have about 148 million US taxpayers, this costs you personally $5.40, assuming these prices. When I asked the kids, would you give up about this much to support understanding where water comes from? It's unanimous. It's absolutely yes. I did this with a second grade class. The teachers were in the room, and not all the teachers' hands went up when I said you could give up a cup of cappuccino. And the students were very upset, and they volunteered to pay for the coffee. So it's not that much to give up to answer one of these really fundamental questions about how you make a world that's suitable for life, because I think this is one of the most important questions that man has been asking for a long time. Are we alone in the universe? Thank you very much.
Thanks so much, Karen. That was a really interesting presentation. And yeah, of course, it does always make us think about life on Earth, water being so incredibly important for that to happen here. Really interesting. We'll open it up for questions at this point. So if any of you would like to just unmute your microphone, feel free to ask questions directly for Karen, or you can type something in the chat box and we'll read that out for you.
Can I talk?
Oh, yes, please go ahead.
So Karen, is the mission being planned now, or designed, or?
Partly. There's several classes of missions. There's the really small satellite missions. There's the Discovery class, which were capped at about 500 million. I think they're going to be at about 800 million the next time around. Then there's the medium-sized missions, the New Frontiers, and then finally the big flagships that are many billions of dollars. So initially, they were going to have the Discovery class missions call soon. And so we were ramping up to put in a proposal to visit a main belt comet. But then with the decadal survey release, NASA decided to swap the order. So the more expensive missions are going to come first, the 1-point-something billion missions, the medium class, and then later the Discovery class will come. So that means we have several years to wait. And so the industry partners that you partner with, such as Jet Propulsion Laboratory or Lockheed Martin, they're gearing up for these more expensive ones and they're putting on hold the Discovery class. So yes, we're planning it, but it's a little bit on hold.
Okay, thank you. That's a shame. I want to know.
And the interesting thing, Discovery class, you can propose whatever you want. The medium class, you cannot. It has to be one of a select few categories that were emphasized in the national decadal surveys. So for that class, they do have things like Venus or a comet nucleus sample return, but we couldn't do a main belt comet.
Thank you.
I should have had Allison set up a poll for how many would pay $5.50, or if we had to double it because of inflation, $10 to learn about water, where water came from. People generally supportive of that. This isn't per year, this is one time.
Anytime.
I'm seeing some thumbs up. Only 2 people would support $10 to learn where water comes from.
I'm guessing that most people who signed up for your talk today would probably be pretty happy to support that. We have other questions from our audience. I'll ask you something that might be pretty naive, given that I'm not a physicist or an astronomer, but you had mentioned Jupiter as one of the potential sources or likely sources of Earth's water. Are there other large planets or other bodies in our solar system that would also be potential donors?
Well, it's not that it is the source, it's the biggest body in the solar system other than the sun. And when you have something really small, if it's on the inside, it would certainly catch up to it. But if it's on the outside, it's going slower than Jupiter, and Jupiter would catch up to it in its orbit. And then when they're close together, the gravity of Jupiter will alter the orbit, and it could toss it inwards, or it could eject it from the solar system or put it in the Oort cloud. And that may be why we see interstellar visitors. It's part of this process going on in other stars, knocking these tiny remnants out of the solar system completely. So Saturn could also do this, but it's not as big as Jupiter, and it's not as close in. But any of the giant planets, anything little that gets close to it are going to get tossed around. And so what we're looking at is icy planetesimals that formed anywhere from, say, the Jupiter out to the outer solar system. It could have come from anywhere out here and gotten thrown inwards. So we want to sample something that was trapped that we can look at and say, aha, the chemistry matches this distance in the solar system, or it matches this distance, and we can understand where we may have harvested our water from. So in that scenario, does it require that we have an organization with rocky planets inside and giant planets outside? That's a big question. And if the answer is yes, then maybe life wouldn't be as common as we think it, or we would like it to be.
There's a question in the chat.
Yeah, just going to read that out. Thank you, Rob. So Deborah has a question. Would main belt comets have any orbital signature that would differentiate them from main belt asteroids?
No, they look exactly like main belt asteroids. And so the only reason that we note that they're different is they have tails. Now there's a bit of caution one has to make, because asteroids are often colliding with each other. So just because you see a tail on something doesn't mean there's ice, because they collide and this will create debris that will image from the ground and it will look like a tail. But these orbits aren't perfect circles. They're slight ellipses, which means sometimes they're a little closer to the sun, sometimes they're a little bit farther. So some of these main belt comets show a tail developing only when they're their closest point to the sun And every time they come close to the sun, they develop a tail. So either that asteroid is extremely unlucky and it keeps getting hit, or more likely it's ice that's sublimating and creating the tail. And of course, with the recent missions with the sample return, especially from Ryugu, the Japanese mission, when they brought the meteorite or the sample back, it's very water rich. Didn't mean it had ice in it, but the water's locked up in the minerals. So I suspect the entire outer asteroid belt is quite wet.
Very good, thank you. Any other questions from our audience today? Okay, well, if not, I'd like to thank Karen again for her webinar. It's always great to have you here and we appreciate the time. Thank you for a wonderful webinar. So we'll end our Q&A session at this point, and I'd like to thank you all for attending, and I'll look forward to seeing you all soon. We're going to have our next event on Wednesday, December 21st, so coming up just a few days before the winter holidays, again at 2 p.m. Hawaiian Standard. It's going to feature a repeat performance from Dr. Rob Jedicke from, again, the Institute for Astronomy. And he's going to be returning to speak on Einstein versus Santa, his Santa breaking the laws of relativity. So looking forward to that presentation very much. Watch your inboxes for your invitation to the event. Thanks again for attending. I hope you have a wonderful rest of your day or your evening. Aloha.